Good morning. This is Mr. Reynolds, and today we want to learn about some oxidation reduction reactions in chemistry. And it kind of goes along with terms that you hear in the healthcare industry right now when you hear ads on TV talking about free radicals and antioxidants. It really goes along with oxidation reduction reactions. And you actually know a lot more of this stuff than what you think right now. So let's move into that. Okay, whenever there's a chemical reaction, whenever two things bond together, and you've named different compounds, molecular ones, ionic ones, ternary ionic, whenever they, let's focus on the ionic ones where electrons are lost and electrons are gained. That'll work best for getting this in your head right now. But whenever an electron is lost and then another atom gains one, one thing is oxidized, one of the atoms is oxidized, and the other is reduced. Okay, that's why they have the dash between it, and they call them oxidation reduction reactions, or they might say redox reactions for short, where it's a combination of these two. Okay, and basically, if something gets oxidized, and they named it oxidation because a lot of times it's oxygen that's bonding onto something, okay? And you learned this before with periodic table that oxygen is known to bond to every single thing on there, and that's why they had to change the name of those column 18. That was the name was inert gases. They thought it just sat there doing nothing. There was no bonding going on, and then they realized, oh, krypton does bond to oxygen. Neon does bond to oxygen a little bit, and so they had to change them. Since there was some reactivity there, they had to change it to the noble gases. Okay, so that's one thing that you knew from before, but oxygen is known to bond to everything on there. So, and just like that, it's bonding to all your tissues if it's exposed to that, and that can break those down. So a substance gets oxidized if it bonds to oxygen. Okay, we've got three things I'm going to list here on each side. If it bonds to oxygen, okay, that's the entire atom. If it loses if it loses electrons, this basically is the same thing. We may see it differently though. And a lot of times in biological systems, if they lose electrons, actually it's losing. If it loses a hydrogen, that's also losing an electron. Okay, we said in biological systems, this hydrogen is a big deal. It's one proton, one electron, and if you really want this electron, if that's what you're after, yeah, that's tough to control unless you have it in the form of a hydrogen atom. That's one electron flying around this first shell around this one proton. This hydrogen atom is a controlled electron. It's a controlled electron. So biological systems use that a whole lot. When you burn up glucose in the mitochondria, it's some of the hydrogens are packed. There's a hydrogen transport chain, electron transport chain. There's hydrogen carriers. Um, there's some hydrogen carriers that are reduced when they're bonded onto electron. Okay, so the opposite. Something is reduced when we do the opposite. So if we lose an oxygen, that substance is being reduced, and the opposites of these also. If it gains an electron, if it and we said electrons, well, if it gains a hydrogen, that's gaining an electron also. Okay, so those are the three situations that make it either the substance being oxidized or it's being reduced. So on the next slide, let's get an example. Let's get a couple examples here. Let's do an ionic compound, magnesium oxide. Okay, we know that magnesium loses a magnesium can lose 2 electrons. When you sketch it out, which you've done before, so let's do it. 12 protons, 12 neutrons. It's got 3 shells. Okay, if you look at periodic table, 2 electrons on the first, 8 on the second, and then 2 on the third. And since it's a metal, the first chance it gets, it's going to lose those 2 electrons. Okay, that's how we get the +2 charge. Okay, by losing those 2 electrons. Oxygen, on the other hand, 8 protons, 8 neutrons. I'm going to try to sketch a little bit smaller because it's only 8 protons. 2 shells. 2 electrons on the first, 6 on the second. The first chance it gets, it's going to gain 2 electrons to get that stable octet. Oh, and so if we do the math, it had 8 protons, it had 8 electrons, and it gained 2 more, so that's 10 electrons. Oh, that overall gives it a -2 charge. Oh, okay, and oxygen is going to gain that. So one magnesium loses 2 electrons, one oxygen gains those 2 electrons. So the chemical formula is MgO. All right. When we look at this, we see that the magnesium is bonding to the oxygen. Okay, the magnesium is being oxidized because it's bonding to the oxygen. It's also losing electrons. Okay, the oxygen is being reduced. Okay, if one thing's oxidized, the other's reduced, and it's always this situation: oxidation, reduction. Okay, for oxygen being reduced, it's gaining electrons. Okay, so this is the reduced substance. In sodium chloride, sodium loses 1 electron, chlorine gains 1. Sketch them out. Sodium was 11 protons, 12 neutrons for mass of 23. It also had 3 shells. It's in column 1, so its outermost one had 1. It had 2 on the first, 8 on the second, and then the 1 electron on the third shell. It's a metal, and it is going to lose that the first chance it gets. Okay. Chlorine was 17 protons, 18 neutrons for mass of 35. Had 3 shells also. 2 electrons on the first, 8 on the second, and 7 on the third. It's a halogen. The first chance it gets, it's going to gain 1 more electron. So it's got that stable octet. Okay? And they have different charges. Okay, let's look at this one. The sodium, the metal, loses an electron. It's going to be oxidized. The nonmetal, the chlorine, gains an electron, so it's the substance that's being reduced. Okay, so again, oxidation, reduction, reactions. Okay, you've already done the bonding on this. This is some new words coming at you. Okay, whenever one thing is oxidized, the other one bonding to it is reduced. All right, and let's go on to this healthcare field these days. You hear a lot of talk about free radicals and antioxidants. Okay, this is stuff you can take with you the rest of your life on it. Free radical. Boy, that even sounds bad. Free means this stuff is floating around on its own. It can bump into and bond on anything that it wants to. Okay. Radicals. Radicals even sounds bad. So free radicals, bad. Doing something radical against the grain. Antioxidants. We've mentioned before that oxygen bonds on. If oxygen bonds onto something, it can break it down. Okay, so that's not good. So things that combat that, antioxidants, prevent things from breaking down. So antioxidants, good. Okay. As we go on with it, let's just. A free radical can pretty much be anything. So any substance that if it bonds onto something else, actually, let's stop for just a second there. Okay, let's start off with a free radical, just to try to get some kind of picture in your head. And there's a number of ways we could do this. Let's picture this damaging, almost something like a bullet. And we're going to use this little triangle as a bullet. Let's say this is a free radical. And if it if it hits a tissue, it can change it. It can damage it. It can put a hole in it. It can damage the thing. It can tear it apart. Okay, so free radical, and they might do it by just bonding to something also. If a free radical bonds onto a substance, once it bonds right here, that may change it. Okay, and let's say this thing now looks like this, and that makes it non-functional. Okay, that's a problem. All right, usually free radicals, they can tear some things apart. If we're talking about cells in your lungs, in your heart, in your blood vessels, free radicals, like we said, bad. They cause some damage to it. They can put little holes into things. They can damage things. Okay, antioxidants. An antioxidant is usually a substance that could tie up one of these free radicals so it's not harmful. So an antioxidant might look like something that something like this, where it fits right into it and basically plugs it up. Okay, so here's my antioxidant, and now this free radical, it can't do anything. Okay, so it can either kind of grab the thing and hold on to it, so the free radical can't do any damage. An antioxidant might do different. Antioxidant might do this. It might bond onto. It might be something else that just that bonds onto this a little bit, making it non-functional. Okay, it can't work anymore. The antioxidant might be something that that basically breaks the free radical apart. Okay, it just breaks it into a couple different parts that are now no longer functional, where before it was, and now it's broken apart and it doesn't work. And on to the next slide on it. So in you, they think that free radicals, different things, bonding onto things that can damage some of your lipids, some of your fats, some of your proteins. And they're doing a lot more linking of different diseases to these things also. And it can damage your DNA. Antioxidants. They're saying, oh, gee, guess what foods they say are high in antioxidants? You've always known this. To eat these things is supposed to be good. Your different fruits, different vegetables, they're saying are high in antioxidants. And one thing that I've seen just hitting the market now on TV ads for health stuff, I hear them talking about beet juice a whole lot, where they get some powder of that. They show people how to make basically some smoothies out of it or something in a blender, and put some beet juice powder in there, and it's supposed to be really, really, really high in antioxidants. Like I said, they can tie up any of these free radicals, and if these free radicals do damage some of these things, and so if it damages DNA, hey, we're talking about different types of cancers in pretty much any cells. Damaging some of the fats. This is they're linking arterial sclerosis to this. Okay, where the buildup of fats inside your blood vessels. So if this is the case, yeah, you know what, they might be onto something here. So look at this stuff down the road as you go on with things, okay? So take this with you as you go. Thank you very much.